so according to this, this is time to start. Let me go back here for a second and introduce, as all of you know, this is the online SPICE-SPIN+X seminar series. This is a joint effort between the Spin Phenomenon Interdisciplinary Center that I lead together with Karen at Racetrack and the collaborative center, research center of Spin+X between Kaiserslautern and Mainz, whose the speakers are Martina Schliemann, Burkhard Hillebrands, and Matthias Chloe. This is in the format of a webinar, meaning that the attendees that come in don't have immediate, you can only watch who is speaking at the time and the shared screen. But you can write your questions, and then if there is immediate questions that I can answer, I will try to answer them during the talk. But I would usually not interrupt the speaker, in this case, Stuart, during his talk, unless it is something vital that I feel that it needs to be a quick answer and go on. But keep the questions on, writing them, and then later, once we're finished, I will hand over the speaker rights that you can speak directly and ask your question directly to Stuart afterwards. And so far, it has not been a problem of any attendee misbehaving or trying to abuse the system. But if you do, just so you know, I will have to kick you out of the system. And again, please check out the different talks that we're going to have next week. Amir Jacobi will tell us about magnets as probes with strongly correlated electron physics as well. And later on, we have a couple of other speakers. And if you so wish to also speak or have a suggestion of a speaker, please let us know. So with this, I just wanted to take 1 minute to introduce a person that really in Spintronics needs no introduction. He is probably the most famous researcher in the whole of Spintronics, and the one that we have to thank the fact that we can have this Zoom and the cloud computing and many other things, because it's difficult. It's not often that you can point to a particular researcher as the one responsible for such breakthroughs, but it is in this case quite known and also acknowledged by the fact that he obtained the Millennium Prize in 2014 for essentially 1,000-fold increase in the hard disk data density that allowed for the cloud computing that we enjoy today. He joined in 2014. We all both moved at the same time to Germany. He's now a Max Planck director in the Institute of Max Planck Institute for Microscopic Structure Physics in Halle, as well as an Alexander von Humboldt professor. And the list of prizes is longer than anybody's CV that I know of. And besides these breakthroughs, he also has been researching and pushing an idea of what to do next in terms of the racetrack type of memories that can have the potential to revolutionize many of the physics that we'll do. So with this, I'll stop here. And Stuart, I'll let you go ahead and share your screen and go on from there. So thank you for giving the talk.
Well, thank you very much, Gyro. I guess you can all hear me. I'd like to thank Gyro for giving me this opportunity to say a few words about chiral spintronics. And this is a subject that is extremely interesting and involves non-collinear spin textures. And I want to particularly discuss their application to racetrack memory. This you can see here is a picture of Halle. I joined the Max Planck Society 5 years ago and became director here at the Max Planck Institute of Microstructure Physics. And also I'm associated with the Martin Luther University, where I'm a professor. So first I'd like to just—
Actually, hang on, Stuart, I think you are sharing the wrong screen, the white screen of the— can you share the screen of your PowerPoint?
Yeah, I'm sharing my PowerPoint. No?
No, I think it's the
yeah, I try again to share screen. Oh, whiteboard. Microsoft.
Yeah, not the whiteboard, but the PowerPoint, yeah.
Oh, very good.
Excellent. Now we get going. Okay.
Oh, I start again?
Go ahead. Now you can start again. Go ahead.
Okay, well, I'm sorry about that. So anyway, so I'd like to tell you a little bit about chiral spintronics, an exciting field of non-collinear spin textures, in particular application to racetrack memory. And as I just mentioned, you probably could hear me. I've been at the Max Planck for almost 5 years. And during that time, I've been fortunate in inviting and hiring a lot of people, postdocs and PhD students, to carry out research. And these are some of the people involved in some of the research that we're doing here, which mostly focuses on spintronics and on ionetronics. But in general, building structures artificially, atomic layer by atomic layer, using a variety of thin film techniques, as well as making thin layers, as you will see, from bulk crystals. So the people involved today in this work, I want to list here. At the top is Cheng Ping, Rana Abe, Ajaya, Robin, and Peter Werner at the Institute. And I also want to strongly acknowledge Claudia Felser and her group at the Max Planck Institute in Dresden, and in particular Vivek, Roshni, and Parul, who've prepared for us fantastic single crystals with which some of the work I'm going to present today is involved. I'd also want to acknowledge Birger Goebel, a student of Ingrid Mertig at the Martin Luther University, who carried out some very nice theoretical simulations. And finally, I wanted to acknowledge Sihon Yang and Chirag, former members of my group where I used to be at IBM Research in California. I want to give a very general introduction initially to spintronics, which is a field of research. It's about 25 years old, and its interest lies both in fundamental science, in particular of spin currents, how to create and manipulate and detect them, and how you could use these spintronic effects to create new applications in memory and computing technologies especially. And my early work in this field involved inventing a sensor. We called it a spin valve sensor for detecting tiny magnetic fields, and which is used even today in magnetic disk drives for detecting magnetic bits. And this spin valve sensor was basically a sandwich of two magnetic layers separated by a metallic layer, and the physics involved was that of giant magnetoresistance, spin-dependent scattering. But the same structure and all of the spin engineering phenomenon that we used to create it is now involved in similar structure, a magnetic tunneling junction, and you can see this in this cartoon. The pink and red layers on the right-hand side correspond to magnetic layers, typically perpendicularly magnetized, and the gray layer is an insulating layer. The electrons tunnel from one magnetic layer to the other, and the tunneling is strongly dependent on the spin of the electron via both the tunneling matrix elements through the tunnel barrier, as well as the spin-dependent density of states within the respective electrodes. This tunneling junction then has been used as a sensor for about the last 10 years. And in 1995, we and Jagadish Mudera proposed we could use the same tunneling junction as a memory element. The information is stored simply as the direction of the magnetization of one of the layers. And because of this very, very strong tunneling magnetoresistance, which means the resistance of such a device depends strongly on the relative orientation of the two magnetic electrodes, these pink and red layers, pink and blue layers, we can easily detect the state by passing a tiny current. I want to just briefly discuss the evolution of these two spintronic technologies. I think it's very interesting. In the case of using a spin valve and subsequently a magnetic tunneling junction as a device to sense magnetic fields within a magnetic disk drive, it took only less than a decade from the discovery of giant magnetoresistance and my own work on discovering oscillatory interlayer coupling, giant magnetoresistance as a general phenomenon, and discovering that cobalt copper gives rise to large effects at room temperature, whereas the original discovery was made at very low temperatures in single crystal films and in very, very large magnetic fields. Then this only took a small number of years before it had an immediate impact. And within 3 years of its introduction, initially by IBM, it was used widely by the whole industry and could enable a very rapid increase in the storage capacity of magnetic disk drives by 10 times within 1 or 2 years. It had a dramatic impact. As I said, in 2007, the basic physics switched from spin-dependent scattering, giant magnetoresistance, to spin-dependent tunneling, but the essential spin-engineered structure remained the same. Now today, in magnetic disk drives, the evolution has slowed down considerably, and we need to do something else. And partly this is because the magnetic disk drive is innately a two-dimensional technology where you store information in magnetic bits in a single magnetic film. I want to compare that with magnetic random access memory, MRAM, where you use essentially similar magnetic tunneling junction is designed to have slightly different properties. And then the idea is, as I mentioned, we could use this to store information. And we proposed this in 1995 when the magnetoresistance of these devices was only a few percent at room temperature. Within 3 years, we demonstrated 80% was possible, and we could reduce the resistance of the tunneling junction devices at that time by more than 100 million times to make it useful for a MRAM application. And we demonstrated that in 1999 with reading and writing speeds of just a few nanoseconds. And then later on in 2005, we demonstrated at IBM a complete 16 megabit demonstrator in 180 nanometer CMOS. At that time, the tunneling junction device states were switched by applying tiny magnetic fields through currents passed through copper lines next to the tunneling junction devices. But at the similar, around about this time, it was discovered you could actually pass a current through the tunneling junction, and the spin polarized currents carry spin angular momentum, which can be used to apply torques and can be used to switch the magnetic moment within the tunneling junction itself. And this essentially is the essence of today's magnetic random access memory using something called spin transfer tunneling effects. And it was only last year that Samsung announced a high performance foundry 28 nanometer CMOS technology of this type. And its application is the foundry technology where you would build the MRAM as an embedded memory to replace what was embedded DRAM, because that technology could not scale. And that is in essence the potential advantage of MRAM. It can scale to smaller dimensions than is possible with other charge-based memory technologies. Just wanted to compare then these two technologies, and you can see it's taken 25 years in the case of MRAM to go from the idea to the implementation. Now I want to talk briefly about, I think, what is a type of memory technology that could replace the MRAM and nearly all existing memory technologies. And this is something I proposed more than a decade ago. I call it magnetic racetrack memory. And as you can see in the cartoon on the middle of the foil, you have a vertical magnetic nanowire, nanometers in width, but microns long. And the blue and red regions are magnetized in opposite directions. And the concept was that if you pass current through this homogeneous magnetic wire, you can move all of the walls between the red and blue regions in the same direction synchronously. And then in so doing, you can put, let's say, 100 or 200 bits of information in a single nanowire and increase the performance or the storage capacity by 100 times compared to any conventional memory technology. And what's exciting is that when I first proposed it, this basic concept of manipulating domain walls with current wasn't demonstrated. And we did that within a few years. It took quite a few years. And so I want to just briefly discuss the evolution of racetrack memory, this concept, from a concept to an actual device over the last decade. And I'm not going to do that in too many details because it would take too long. But originally, the concept was to use soft magnetic materials. And this is, if you like, racetrack memory 1.0. And in those cases, you'll pass current into the wires, and the domain walls move, and they move in the direction of the flow of spin angular momentum created by polarizing the charge current through spin-dependent scattering within the magnetic layer itself. And when you completely transfer all the spin angular momentum from the current to the domain walls, the maximum potential velocity is about 100 meters per second for current densities that don't significantly heat the racetrack. That's what we demonstrated in Racetrack Memory 1.0. We could achieve nearly complete transfer of the spin angular momentum from the current into the magnetic system. That was quite a surprise. It's achieving velocities of about 100 meters per second. Well, then it turns out that in soft magnetic materials, because there's no anisotropy, the size of the domain walls is determined by magnetic exchange, Heisenberg exchange, and by dipole fields. And so these are relatively large domain walls, which are highly elastic. So Racetrack Memory 2.0 was rotating magnetization from in the plane to out of the plane by engineering thin film structures. and shrinking the size of the domain walls by more than 100 times, let's say from a few hundred nanometers to a few nanometers. And then it turns out, again, the domain walls moved at roughly the same velocity, again in the direction of the flow of spin angular momentum from internally scattered and created spin currents. So the next two, if you like, generations of racetrack memory involve new physics that was unanticipated. And in particular, in Racetrack Memory 3.0, we created current, the spin current, in a very different way by something called the spin Hall effect. And I want to discuss that briefly. And similarly, in Racetrack Memory 4.0, which makes the technology useful, is that we could create a racetrack in which the dipole fields from the individual domain walls are eliminated by building something called a synthetic antiferromagnetic racetrack. And this is actually something I invented in the early days of the spin valve technology. And it was even used in IBM's very first spin valve in 1997, because it creates extremely stable structures and it eliminates long-range dipole fields, which otherwise cause interaction between magnetic layers, especially on a nanoscale, where these dipole fields increase inversely with the size of the device. So we published quite a few papers over the last few years on Racetrack Memory 3.0 and 4.0. I want to just discuss one or two elements of the technology. In particular, I mentioned already that we create racetracks in which the magnetic moment is perpendicular to the racetrack or the thin film. And we do this by simply creating interfaces. So you take a multi-layer of cobalt and nickel. Individually, they're extremely soft magnetic materials, but by creating interfaces on the atomic scale, where the cobalt and nickel layers are just a few angstroms thick, the interfaces break the symmetry and give rise to large perpendicular magnetic anisotropy. And this was a subject that was really extensively studied 30 years ago. And a wide variety of magnetic multilayers display this property. That's important. But at the same time, for racetrack, what is particularly important is that you build this heterostructure on an underlayer, shown here in orange, which is formed from a heavy metal, for example, platinum or tungsten. And then you break the symmetry, the center of symmetry of the system, so that this can give rise to several effects. Most importantly, it gives rise to something called the Dzyaloshinski-Meria exchange interaction, which means that through spin-orbit coupling, for example, in this cartoon, the dark green layer, which is a cobalt layer, sitting on top of the underlayer, let's say platinum, cobalt moments interact and are exchange coupled through platinum. And because of this spin-orbit coupling phenomenon, the broken symmetry, it leads to an exchange interaction where the magnetic moments in the cobalt layer want to be aligned, not parallel to one another, but perpendicular to one another. Moreover, they're aligned in a vector fashion. So the Dzyaloshinski-Meria exchange is a vector exchange, which means that the moments want to be not only perpendicular, but they want to be clockwise or anti-clockwise oriented, as shown in this cartoon. So the cartoon shows a racetrack with blue and red domains pointing up and down. And in the middle, when the moment rotates from up to down in the domain wall that is shown, in the middle of the domain wall, the domains will either be clockwise oriented if they're, for example, the cobalt layer is grown on platinum, or anti-clockwise oriented if the cobalt layers are grown on tungsten. And this is shown in these cartoons. What does that mean? As you move along the racetrack, the red moment rotates down into the blue moment, and you'll notice that it rotates in a plane perpendicular to the domain wall. This is a nail domain wall. And when it rotates from a blue to a red direction, then you can see in the middle of the domain wall, the magnetic moment will be in the opposite direction, again aligned along the racetrack. So there's a chirality associated with these domain walls. And this, in some sense, is the first use of a chiral spintronic phenomenon. And as I said, these domain walls can be clockwise or anti-clockwise, depending upon the nature of this Dzyaloshinski-Meria interaction, which is really an interface interaction. And related to that, then, at that interface is another very interesting interaction, where there is a proximity-induced magnetization. The cobalt layer causes a moment to be developed in the platinum layer. This is an enormous moment. So in typical racetracks, which are shown here, would consist of only 2 cobalt layers separated by 1 nickel layer. The cartoon shows more layers, but typically we'd only have 2 cobalt layers separated by 1 nickel layer. Then 50% of the magnetization of that cobalt-nickel-cobalt sandwich would be developed in the platinum underlayer. It's a very important effect. So these are the several effects that we need to make the racetrack work. And the fourth effect, which is very important, is something called the spin Hall effect. So you're all familiar with the normal, ordinary Hall effect shown on the left-hand side. A current in the presence of a magnetic field through Lorentz forces causes the electrons to be moved to the left or to the right. You have a charge buildup. And this is the normal Hall effect. But in the case of certain materials with strong spin-orbit coupling, in the absence of a magnetic field, you get a buildup not of charge, but a buildup of spin. And you have an accumulation of spin-polarized electrons on one side and the other side are in opposite directions, as shown on the top right by the red and blue arrows. And it turns out this is also then a chiral phenomenon, where a current flowing in one direction produces a spin accumulation around the circumference of that wire, pointing either clockwise for one direction or anti-clockwise when you reverse the current. And at the same time, you could change, by changing the material from platinum to tungsten, for example, you can change the sign of the Hall, the spin Hall effect, or the spin Hall angle. And so a very important number is the conversion efficiency of the charge current to the spin current. And typically this was thought to be extremely small until a few years ago. In fact, the spin Hall effect was only observed 15 years ago by David Oschlom's group in a semiconducting material. And they observed it was a tiny fraction of a percent. And it was believed to be even very tiny in metals until quite recently. And I wanted to point out here, then it was a very beautiful work by the Cornell group of Dan Ralph and Bob Lerman, where they were the first to report significant effects, for example, in a certain special crystal form of tungsten, which is obtained in ultra-thin films and tantalum. When they first reported it, it's of the order of a few percent. Now it's of the order of 30%, and platinum, for example, is 20%. So these are huge numbers compared to what it was believed and what was first shown in gallium arsenide. As I said, 15 years ago, it was 0.0001, and platinum and tungsten today of the order of 20 or 30%. And now there's some other interesting materials. We've shown, for example, that chiral antiferromagnetic materials give rise themselves to a significant intrinsic spin Hall effect related to the chiral antiferromagnetic structure. We demonstrated this in manganese 3 iridium, but you could also anticipate large spin Hall effects in certain topological insulators and topological metals. And
Stuart, quick question. Which slide are you on now?
I'm on charge to spin conversion via the spin Hall effect.
Okay, good.
That's okay?
Yeah, that's also good. That's good.
Yeah, I was just going to give, yes, I'll speed up, sorry. Wanted to say here simply, without going into lots of details about how we measure it, but the magnitude of these spin Hall angles is very significant and can be usefully applied to create significant spin currents from charge currents. But I wanted then finally, with regard to racetrack, to mention that truly, and this was, I think Thomas Jungwirth gave a very nice talk about antiferromagnetic spintronics, I think the first talk in this series, and a challenge in all magnetic nano elements is controlling the large fields, the dipole fields from the moments that are generated at the edges of magnetic wires or magnetic entities. And these fields are extremely large, up to 4 pi m, the magnetization of the material. And on the nanoscale then can cause significant interactions between magnetic layers within a structure or between devices, one device and another device. And so, as I said, you could use something called this oscillatory interlayer coupling that I discovered many years ago. And shown here in this cartoon, this yellow layer is a thin layer of ruthenium, which essentially is used to couple two racetracks above and below, shown as these this blue-green layer, which is cobalt, nickel, cobalt. And the two moments then can be coupled antiferromagnetically, as shown in the cartoon. And in fact, you can obtain a mirror image of whatever is the magnetic profile of one racetrack in the opposing racetrack. And by suitably designing these two layers, you can essentially eliminate all the moments. So the net moment in this synthetic antiferromagnetic racetrack goes to zero. Nevertheless, of course, locally, there's magnetization. And that's what's nice in these synthetic antiferromagnet surfaces are still magnetic, but in aggregate, the volume has no net magnetic moment. And then we discovered unexpectedly that these structures, you pass current, and the domain walls would move 5 to 10 times more efficiently than in the respective single antiferromagnetic, single racetrack, or if we change the interlayer coupling ruthenium thickness slightly, so the coupling changed from antiferromagnetic to ferromagnetic, then the speed would be 5 to 10 times lower. So this leads to speeds exceeding 1 kilometer per second for useful currents, and this makes racetrack memory super interesting because this means you can imagine picosecond time devices where you could move a domain wall 100 nanometers in a picosecond. Very interesting for ultra-fast memory devices. So I just want to show you here. So again, without going into many details, we can, and so to date, most of our work on these, looking at the current-induced motion of domain walls is in racetrack devices or nanowires, horizontal nanowires are shown here, where they're of the order of 2 microns wide. So we could use magneto-optic Kerr effects or optical effects to detect the domain walls. The upper shows you a series of domain walls moving at 300 meters per second, and the lower one now moving, you can see a synthetic anti-ferromagnetic racetrack where the domain walls are moving at more than a kilometer per second. So in summary, what's interesting is in these, this is a chiral, truly chiral spintronic phenomena, where we have chiral domain walls set by Dzyaloshinski mirror exchange across an interface with a heavy material with strong spin-orbit coupling, and we use spin currents from the spin Hall effect, which themselves are chiral. So these are very interesting interplay of chiral spintronic phenomena. But I want to now just briefly discuss in the next part of my talk, not multi-layers, but rather I want to briefly discuss compounds, and in particular focus on the Heusler family of compounds. And the Heusler family of compounds is a huge family of ternary or quaternary materials, which are a wide range of properties, including some which are magnetic. Usually they're cubic. The structure is that of 4 interpenetrating FCC lattices, but those materials which have, again, strong, heavy elements, through spin-orbit coupling, the structure can be distorted, and it's tetrangly distorted, and the structure gives rise to a magnetization, which is out of plane along this tetrahedral axis. So it's a strong interplay between the magnetism and the structure. And at the same time, those same heavy elements, through the same Dzyaloshinski mirror interaction, can give rise to a non-collinear magnetic structure. So this work I'm discussing is the work we're doing closely with Claudia Felser and her group, where they make these fantastic single crystals of a wide range of materials. And the materials of interest are manganese 2, rhodium, iridium, or platinum tin compounds as shown here. And the concept is, if you look in the middle tetragonally distorted structure, then you can see there are layers of these manganese atoms. They're shown as blue and red atoms, and they have different environments, and so the moments are different. And interestingly, in these structures, these manganese moments in the blue and red respective sites are coupled antiferromagnetically, leading to a net ferrimagnetic system. This system typically has Curie temperatures above room temperature, And shown on the bottom, you can see in low magnetic fields, the magnetization undergoes a transition at approximately 100 degrees Kelvin in manganese 2 platinum tin, where the structure goes from the simple ferrimagnetic structure to what is believed to be the non-collinear magnetic structure shown in the cartoon on the top. And this was some work that was published in 2014. In the same structures, you can see evidence perhaps for other types of interesting structures through something called the topological Hall effect. I don't want to discuss that in any detail, but the goal of this work was to search for something that's called an antiskyrmion. And again, this is a chiral magnetic structure. I just wanted to remind you and put this in perspective of the skyrmion. So it turns out that more than 10 years ago, Christian Fleiderer discovered in a particular material, manganese silicon, that he discovered something on the left, this block skyrmion. What does that mean? That simply means that the magnetic state of the system under particular magnetic fields, relatively high magnetic fields, and very close to the Curie temperature, he discovered that you could see an array of block skyrmions. What is that? That means the magnetization in the system, instead of pointing in one direction, breaks up into small magnetic nano elements in which the magnetization in each of these circular elements is pointing in the opposite direction. And therefore you have a circular boundary, a domain wall, and this domain wall is chiral, and it's also a nail wall. It's very closely related to the nail. This is a block, in this case, a block skyrmion. So if you look on the right-hand side, you can see it's actually been found in only a small number of systems, until recently only in insulating systems at low temperatures, a nail skyrmion. This nail skyrmion is closely related to the chiral domain walls I discussed in Racetrack. In this case, this circular boundary consists of a magnetization that's rotating from the perpendicular direction on the outside to the opposite direction on the inside, and the magnetization rotates in a plane along the radius of the skyrmion. That's a nail skyrmion. But in the block case, the magnetization rotates from the up to down direction in a plane which is perpendicular to the radius or along the tangent of the skyrmion. I think you can see that in these cartoons. Now, what was interesting, theoretically, it was predicted that certain types of magnetic systems with strong Dzyaloshinskii-Maria exchange, with a certain symmetry, a more complicated symmetry, would show a ground state that could consist not of a block or nail skyrmion, but an antiskyrmion. And an antiskyrmion is more complicated, as shown in this cartoon. As you go around the periphery of this circular device, the walls change from a nail type wall to a block type wall, back to a nail type and a block type. And each time the wall type varies, the chirality, whether it's clockwise or anti-clockwise, also changes. So it has a much more complicated structure, which is determined by the symmetry of this exchange interaction. So now, how do we detect these objects? And one way, very useful way to detect them is with Lorentz microscopy. Shown in this cartoon, you simply pass a very high energy beam of electrons through a layer thin enough that the electron beam is transparent, and you look at the deflection of the electrons through Lorentz effects. And so if you have an in-plane magnetic moment, as we do in these block and nail skyrmions and anti-skyrmions, there's an in-plane component of the magnetization in otherwise these perpendicularly magnetized materials in the domain walls. And in the case of the block skyrmion, the Lorentz forces causes the electrons beam all around the circumference of the object to be deflected either inwards or outwards. And so in the Lorentz micrograph, you will see a circular spot of increased or decreased electron intensity shown on the left. This is a simulation. So here we've carried out micromagnetic simulations of these structures and then carried out calculations of these forces on the electron's beam and how the image would look in different focal planes or defocused planes. The nail skyrmion, on the other hand, causes the electron beam to deflect it around the circumference. So effectively, you don't see anything for normal incidence, shown on the right-hand side. But in the middle, the anti-skyrmion, you can see that we anticipate then seeing a more complex forces on the electron beam, and you end up with this clover-like structure of two white regions of increased intensity and two black regions of decreased intensity, as you can see in this middle region. So if we now look at a real structure, and here we've taken this manganese 2 platinum tin Heusler single crystal from Claudia Felser, we've made a thin layer from it, 100 nanometers thick, by using focused ion beam milling. And here you can see in the top row, number A, you can see this is an image of an anti-skyrmion. This is about 100 nanometers in size. This is at room temperature in the presence of a perpendicular magnetic field. But interestingly, if you look here at C, you can see that you have an array, an hexagonal array of these anti-skyrmions. And this array then will evolve as a function of temperature and field. And the rest of these micrographs show different magnetic fields and how the whole array evolves. I don't want to again discuss that in too many details. I want to discuss just one aspect of these anti-skyrmions, and that is how the anti-skyrmions evolve, firstly, from a helical magnetic structure. So if you look here, you can see, what are we looking at? In the top left, you can see, again, a Lorentz transmission electron micrograph for a wedge-shaped lamella, which we've fibbed from a single crystal of this manganese 2 platinum tin. This is work by Abe here in Max Planck. And you can see, if you look here on the left-hand side, you can see black and white lines. Those black and white lines mean the ground state of this system under these conditions of magnetic field and temperature is no longer a uniform, perpendicularly magnetized layer, but rather it forms a helical structure where the magnetization rotates one-dimensionally from an up to a down direction in a sinusoidal fashion. And it turns out in this Heusler material, the orientation of this helical structure is set by the crystal lattice. So I don't know if you can see, but in this image shown on the top left, you can see a region A where the black and white lines are approximately perpendicular to the foil, and in region B, they're parallel. And this is because these are two crystallographic directions which favor the block type of walls. And these two directions have the lowest energy for these helical structures because these block-like walls have less energy. And then you can see for these regions A, B, C, these correspond to three distinct thicknesses of the lamella through which we're imaging these chiral structures. And they show you from the left column, it's in 0.27 Tesla, relatively high magnetic field that stabilizes the magnetization along the tetragonal axis. We're looking along the tetragonal axis. And then it shows you what happens as we reduce the magnetic field. You eventually start to see here in 0.2 Tesla some anti-skyrmions, and then at 0.1 Tesla you start to move into the helical state. And you see at 0 Tesla you can see these two different orientations of these helical structures. Now, depending upon the thickness, the phase diagram can evolve. That's what I want to discuss in a little bit more detail. And in particular, I want to first make the point that what's really nice about the anti-skyrmions in the Heusler compounds, we've seen it in several different Heusler compounds, is that as a function of temperature and magnetic field, they're very stable. So over a wide range of perpendicular magnetic field and a wide range of temperature, you can stabilize arrays of these anti-skyrmions. This is what is shown here, showing you that as a function of increasing thickness from 160 nanometers to 1/4 of a micron, the phase diagram is such that the stability of the anti-skyrmions increases. That's what I want to briefly mention here. And I want to compare that with the archetypical skyrmion system, the B20 chiral system, iron germanium. This is very closely related to the manganese silicon system in which the original discovery of these skyrmions was made by Christian Fleidrer. This is some beautiful work from Yoshi Takura's group. And what they're showing is plotting a similar phase diagram the red regions are where you see skyrmions, and what is plotted is the perpendicular magnetic field and the temperature from room temperature down to lower temperatures. And you can see as you increase the thickness from the top to the bottom, from 15 to 35 to 60 to 75 nanometers, you can see that these red region decreases in size. That's where they see these skyrmions. So the skyrmions become less stable as a function of increasing thickness of this lamella. Now this is in complete contrast to the anti-skyrmion. So this is a very nice work by Zhengbing Ma in my group here in Halle, who explored using micromagnetic simulations. He changed this code, this Ohm's code, so we can have any vector, any type of symmetry of the Dzyaloshinskii-Maria exchange vector. And he compares on the top the B20 structure, the iron germanium or manganese silicon system, which shows skyrmions. And I don't know if you can see, but basically from the top to the bottom, 1 to 18, these are increasing thicknesses of the structure. Each of these layers is tens of nanometers thick. And you can see going from left to right is the perpendicular magnetic field. So the skyrmions are stabilized in a small region of magnetic field and thickness. Whereas for the anti-skyrmion in the D2D symmetry Heusler compound, there's no dependence on the thickness of the lamella in the absence of dipole fields. These calculations do not include long-range magnetic dipole fields. So there is a big contrast, and that's related to the symmetry of this crystal structure, which is reflected in the symmetry of this vector exchange. In the B20 systems, which are cubic, then this means that it will stabilize a twisted magnetic structure in all three directions, and effectively wants to stabilize spherical objects. Whereas in these D2D systems, there is no component of this vector, the Dzyaloshinskii-Maria vector, perpendicular or along the tetragonal axis. And in this case, you, in principle, should find tubes, columnar regions, which are stable as independent of thickness. But an important point is that we discovered that actually both the period of these helixes that I mentioned, plus the size of these anti-skyrmions evolves with thickness considerably. So in Lorentz microscopy, we're limited to thicknesses of the material through which this electron beam can be transmitted. And so here we have showing thickness of a lamella, again formed from this manganese 2 platinum tin compound, where the thickness varies from 40 nanometers to 200 nanometers, approximately. And the period of the helix, which you can see on the right-hand side in this beautiful Lorentz micrograph, this period also evolves. You can see it's thinner, smaller on the right side, and it's wider on the left side. And it changes from 100 to 200 nanometers. So a dramatic change in thickness. But actually, that's at room temperature. But if we want to go to thicker lamella, we need to use a different technique. So then we use simply magnetic force microscopy. We can do this as a function of temperature and in various magnetic fields here. And then we find we basically, you see an image shown on the top left where you can see beautiful helix, the helical structure, pointing with the period, with the Q vector, horizontal and vertical in the top corner. And if we take a line profile on the bottom left, you can see a beautiful sinusoidal profile of the magnetization with a period of 300 nanometers. But as we increase the thickness to 1.6 microns, we see the period increasing further to 500 nanometers. So it's a dramatic change. And in fact, here it's even more dramatic. Now we have lamella that vary all the way from 40 nanometers to 4 microns. And you can see the period of the helix increases from 100 nanometers to more than 1 micron. So now we can see these structures even optically. And shown on the left of 4 is firstly on the top left in A, you can see the lamellar wedge we've made, or Abbe has made. And then you can see in these 3 different magnetic force images, we can stabilize these helical structures in different directions by applying in-plane magnetic fields. And you can clearly see that these helical structures have their oscillation period only in two distinct crystal lattices determined by the underlying crystal symmetry. So this is a beautiful result. And similarly, now by changing the magnetic field, we can stabilize, instead of the helical structure, we can stabilize the antiskyrmions. And in the magnetic force microscope, the antiskyrmions look like single blobs or single circular entities, as shown here. So on the top left, you can see the helical structure, magnetization rotating from up to down in a sinusoidal fashion. And then here, you can see in the other regions, you can see the antiskyrmions over the whole wedge. The wedge thickness here is varying from 0 to 4 microns. And you can see the antiskyrmions are varying from small on the left to big on the right as we change the thickness. So this is amazing. And the maximum size of these antiskyrmions we found so far is about 1 micron. So why is this? And this is this result is totally due to dipole fields. And the dipole fields, the dipole energy completely dominates these thicker layers, the thickness dependence. And we can explain this thickness dependence from the role of the magnetostatic long-range dipole fields. I just wanted to, this is what I wanted to say about the antiskyrmions. So they have distinct properties from skyrmions. They're more stable, they're independent of thickness, but their size can be tuned by thickness, making them technologically extremely interesting for this purpose. And I just wanted to mention, nowadays, there's a whole zoology of skyrmions. Antiskyrmions are still restricted to this Heusler compound. But in the same Heusler compound, we can actually stabilize elliptical skyrmions. Again, this is dominated by dipole-dipole interactions. So they're no longer circular, as in the block and nail skyrmions previously seen, but these have an elliptical structure where the ellipse is oriented with its major axis along these two distinct crystal directions, these helical directions that I mentioned. So this is super interesting. And I wanted to finally mention, yes, the chiral structures now found, these ground states can be found in many different systems. And one I can just briefly mention, again, it's a zinc crystal from Claudia's group, platinum, manganese, gallium. It's not a Heusler compound. It has a trigonal structure. And the structure we've discovered is non-centrosymmetric. And therefore, you actually have an ordered arrangement of platinum, manganese, and gallium. And this, again, through Delizinski-Maria exchange, can stabilize a very unusual nail skyrmion-like structure that we can observe by tilting lamella in the transmission electron microscope. And we can see these are clearly nail skyrmions. And it's the first observation of a nail skyrmion in a metallic system. And these we can see almost to room temperature. So the conclusion is these chiral spin structures are multiple. And even in one structure, you can stabilize metastable states which have entirely distinct structures. But in all cases, the chiral structure and the chirality is intimately linked to the symmetry of the underlying Delizinski-Maria exchange. And another very interesting aspect of these nail skyrmions is, just like the anti-skyrmions, we discovered, again, due to the particular symmetry of these trigonal symmetry, you find that, again, the dipole fields play a role, and the skyrmion size can be significantly evolved with thickness varying here from 100 to 600 nanometers, as the thickness of the lamella is varied from a fraction of a micrometer to several micrometers. And this again is using magnetic force microscopy. This is some very nice work by Ankit. And it turns out these types of skyrmions are very robust to longitudinal in-plane fields. Now, I wanted to briefly mention that. So during this 5 years here, I built up almost from scratch an entirely new experimental capability. And one thing we built, which I think is kind of interesting, is a very elaborate capability for depositing thin films. And yeah, I don't know if you can see the scale, but we have a vacuum tube, which is 10 meters long. It will soon be 12 meters long. And connected, this orange-shaped device, we call it Mango, is a system where we've designed it for accelerating our ability to explore thin film materials. All the source materials are behind differentially pumped gate valves, so we can change source materials whilst the main part of the system is maintained under ultra-high vacuum. And this ultra-high vacuum tube allows us to take wafers or substrates from one of these mangos designed for magnetron and ion beam sputtering to, for example, this shown on the top left. These are two Gen 10, these are molecular beam epitaxy systems, one designed for oxide, one designed for nitrides. And also connected to this system is a angle resolved photoemission system and a pulsed laser deposition capability. And soon we'll have a glove box so we can exfoliate 2D materials and place them onto MB grown or magnetron grown or pulsed laser deposition grown layers. Now I wanted to, the reason for saying that is that I think there's interfaces play such a significant role that creating artificial interfaces gives rise to entirely new physics and entirely new properties. And that's something that we're extensively exploring both in spintronics and in other areas of condensed matter science. Now, if there's time, I wanted to briefly discuss one final comment, which is we can make chiral spin textures, but we can also make spatial spin textures. And I just want to give you one example. This involves something called ionic liquid gating. So we can, of course, gate a conventional transistor by applying large perpendicular electric fields, but you can apply even larger electric fields by using an ionic liquid, which is typically large organic molecules combining a positive and a negative molecule. And by applying a voltage to the liquid, you can cause molecules of one charge type to go to one of the electrodes as shown in this cartoon. And so you basically create a layer of positively or negatively charged molecules on the surface of a channel. Here, an oxide is shown. And this is called an electric double layer, and you can have enormous electric fields created by the ionic liquid and the oxide. And this we demonstrated a few years ago in a paper in Science that we could, for example, in the case of vanadium dioxide, shown on the left, you can see the resistance versus temperature, and just close to room temperature, the resistance of the metallic material above that temperature switches to an insulating material shown by the purple curve. And what we demonstrated was by applying, using an ionic liquid, a large electric field, we could completely suppress this metal to insulator transition, and you develop the red curve you can see, in which the resistance only weakly changes with temperature. So by applying this high electric field, we demonstrated that this was not an electrostatic phenomenon, but rather the electric fields were so intense, we started to remove oxygen from the VO2. We think a tiny amount of oxygen, nevertheless sufficient to give rise to a non-volatile change from a metal to an insulator. So people were very skeptical about this for some time. And so since I came here, we could use these ionic liquids to gate an oxide device within the transmission electron microscope. And the system we chose is this one, strontium cobalt oxygen 3, which is a perovskite. And you can see on the right-hand side, you can see it's a beautiful cubic structure. This is in the transmission electron micrograph. These films of strontium cobalt oxide we've grown by pulsed laser deposition on strontium titanate, shown here. And then using this ionic liquid, we can convert this structure to the structure on the left-hand side, which I hope you can see. You can see alternating dark and light regions, these corresponding to alternating layers where we've removed half of the oxygen. So you form an ordered arrangement of oxygen vacancies, in this case parallel to the strontium titanate. Well, it turns out the one on the left, the strontium cobalt 2.5, is called a brown millerite. It's antiferromagnetic and it's an insulator. And the material on the right-hand side is perovskite, it's metallic, and it's ferromagnetic. So we can switch from one to the other in a non-volatile fashion, as we can see in the transmission electron microscope. So on the left, we start off with the brown millerite, a thin film, and as we gate it, we can actually gate it completely to the perovskite as shown on the right-hand side. And we can see that also from the selected area diffraction of the left-hand side. You can see the unit cell is much bigger than on the right-hand side. And we can, takes a few minutes, but we can transform the complete film from a ionic liquid at the surface deep into the film. In VO2, we've demonstrated up to a micron or so. And in this case, we can demonstrate up to several microns from the edge of the ionic liquid. We can remove the oxygen or put it back by reversing the gate voltage. This is what we're showing. We can inject oxygen ions from the ionic liquid to turn the perovskite, the brown millerite into the perovskite, and we can go backwards. Now we can remove oxygen to turn the perovskite on the right-hand side to the brown millerite on the left-hand side. So what does that mean? Why is this interesting? I think it's interesting because we could use this to create magnetic mesostructures. So what we do now is we take an oxide layer like the strontium cobalt oxygen 2.5, and we put a resist layer on the top, and then we make holes in the resist and we liquidate through the resist, and we then only change the brown millerite to the perovskite in the holes. So we create metallic holes in the middle of an insulating layer, shown here by conducting atomic force microscopy after we've gated the device and removed the resist layer. So why is it interesting? Well, we can create enormously complex layers, and I just want to give you one example. It turns out we've also demonstrated that we can, by changing the liquid gating conditions, we can form the brown millerite with these oxygen vacancy planes either vertical to the substrate or parallel. Each of these are antiferromagnetic but have different structures. And so now we can actually create like a patchwork of regions on the less than 100 nanometers in size. In this case, we've got the two brown millerite, two distinct antiferromagnetic layers shown here with a boundary between them. It's only 5 nanometers wide. And on the right-hand side, we have a boundary between a metallic ferromagnetic perovskite and this antiferromagnetic insulator. And you can see this in the cross-section TM. So we can actually make a wide variety of spatial magnetic mesostructures this way. We can even make a racetrack out of this strontium cobalt 0.2.5, a metallic strontium cobalt 0.3 stripe, and see the domain walls move. And it turns out they move extremely efficiently. So I have no time to discuss that because I see Jairo is waiting for me to finish. So I just wanted to conclude. Chiral spintronics is a super interesting area of spintronics in which we use chiral phenomena, in particular the Delizinski-Mirror interaction, the spin Hall effect, to create both interesting chiral structures, either for racetrack memory or in the form of chiral domain walls, or these chiral objects. We discovered this anti-skyrmion in the Heusler compound, and these are potentially interesting for racetrack themselves. So far, we actually haven't seen the anti-skyrmions move with current, but that's something we're working on. And then finally, just briefly at the end, something we're doing more recently is to create artificial spin textures by using oxide materials in which we locally add or subtract oxygen. And we can do this on approximately the 15 nanometer length scale to create boundaries that are 5 nanometers wide. I think this has a lot of interesting potential to create spin liquids, racetracks, and other types of structures, and maybe chiral spin structures as well. I'd like to thank all my collaborators here at my current institute, with Claudius Institute, Ingrid Batik's group, as well as some of my colleagues, former colleagues at Dublin. Thank you very much for your attention.
Thank you very much, Stuart. Everybody raise their hands to clap for Stuart. That's how we tend to do it here. So you can see all the 300 of some, I think we have about 500 altogether between YouTube and Zoom logged in here. And then you get lots of hands up, so it's very good. So now everybody hands down because I'm going to now ask a few people to ask questions. So let me go first, I think. Let me go here. Igor, go ahead. I'm going to allow you to talk. So go ahead, Igor. You had some questions. Igor Mazin.
Okay, I have to. Yeah, took me some time to unmute myself. I had two questions, but they sort of appeared during the talk. When you were discussing these experimental results from sequence and field dependence on skyrmions, you also showed in the phase diagram, experimental diagram, they only appear at high temperature. Is there any understanding why temperature is important?
Oh, that's a very good question. Certainly, temperature plays a role in that the magnetization will change, and then dipole fields, dipole energies will change. But another thing that can change is the magnetic anisotropy. So typically in magnetic systems, the exchange has weak dependence on temperature, but certainly the anisotropy, which has a much stronger temperature dependence, typically a high order value on temperature, will evolve. So for example, as I showed at the beginning, in these Heuslers, you can see a transition from a ferromagnetic to a non-collinear magnetic state at low temperatures. This is the combination, I think, of the temperature dependence of the magnetic anisotropy and the, in many cases, the dipole energies.
So you don't think that fluctuational physics may play some role here?
Fluctuation physics?
Yeah.
I don't think so. I think it's an interesting question. And of course, what's really amazing is that in these systems, let's say this anti-skyrmion system, you can create many, many, many different metastable states. So in some sense, then once so in that sense, you're right. But once they're formed, it seems they're stable, so they don't fluctuate. But I think that's a very interesting question, and it's actually one that we're closely working on in Racetrack as to, which is not quite the same, but we're looking at fluctuations of the domain walls.
So, Jairo, may I ask my second question?
Go ahead. There's a brief one, which let's say quite a few lined
so
up.
The other question is also, for this, this may be a very naive question, but for these applications, do you need like actual skyrmions defined as a state where this triple product of 3 spins with this current or in continuous representation, so that if M, dm over dx and dm over dz have non-zero triple product, or something simpler like a conical spiral or the transverse conical spiral would also work?
It turns out, it's an interesting question. It turns out, of course, that when you make real nano elements, the confinement of these structures can also evolve the magnetic structures. And so I'm not sure exactly what your question is, but certainly confinement on scales that are reflective of the underlying physics, in other words, the critical length scales within the problem, you can, of course, use those confinement aspects, let's say nanowires, to change the structure. What's important, I think, for, let's say, a technology is you do want magnetic nano elements or structures that are stable, unless you want to take advantage of those different structures, let's say, for computational needs. But I think for memory elements, you probably need to have stable structures, but certainly having many different stable structures that you can access is also very interesting, either for memory or computing technologies.
Okay. So let's see. Let me see. For some reason, this person is not okay. We need to be promoted. Okay. Let me go back to. Sorry, I need to. Philippe Pirot, go ahead and ask your question.
Can you hear me?
Yeah, I can hear you.
Ah, yeah. So thanks a lot for that nice talk. You were mentioning that the induced moment in the platinum, in the cobalt platinum multilayers would play a large role. So is it just that you need to consider that it's there, or is there any physical effect which is important in this context?
Oh, I think it's extremely important because, for example, if you want to look at the Delizinski-Meray exchange, the question is really where is the interface and what is the role of the platinum? So I think this is critically important to appreciate this proximity-induced magnetization. It'll change completely the physics of the interactions.
Okay, so would you consider that the interfaces between the non-magnetic platinum and the magnetic platinum?
Yes, you could. For example, exactly right. It could be, as you know, the susceptibility of the platinum, of course, decays to some decay length, about a nanometer into the platinum. So it's a very significant effect. It's sort of consistent with the length scale, which is calculated to be the spin diffusion length in platinum. It's of the same order of magnitude.
Okay, thanks.
The next question comes from Igor Rozansky. Please ask your question. I think you're unmuted.
Okay, thank you very much for the very interesting talk. A simple question: what are the minimal size of anti-skyrmion to date, and in which system?
Okay, so far the minimal size that we've seen is of the order of, let's say, 14 nanometers. But of course, there's that was in one of these Heusler systems, but you can clearly imagine that they could be smaller by developing systems in which you have stronger DMI interactions. So it's really closely related to the DMI interaction, and in these cases, depending upon the symmetry, understanding the role of the dipole fields.
Okay, thank you.
And by using the dipole fields, you can actually shrink the size significantly. So this is why it's important.
Okay, the next question comes from Helen. Helen, go ahead and unmute yourself, please.
Can you hear me?
Yeah, we can hear you.
Thank you for a very interesting talk. It's, as always, fantastic. I have a similar question which Philippe has asked. So you say that, okay, you said that the platinum in combination with an antiferromagnet can create this DMI interaction.
Yeah. Oh.
You muted yourself, Helen, somehow. You need to ask the question unmuted.
Uh-oh.
I think Helen is having some technology issues, so I'll wait until she resolves them. Yeah.
Okay.
She's kind of muted herself. Let me actually ask, I think it's Stavros, I'll allow Stavros on. Stavros, can you unmute yourself and ask your question? Go ahead.
Yeah, I would like to ask something. Well, I understood at some point that in the material that the DMI is suitable for anti-skyrmions, also Bloch skyrmions were observed,
yeah,
but they were of elliptical shape.
Yeah.
Okay, that seems very interesting.
And the elliptical shape, as I mentioned, it's the ellipse is directly connected to the underlying crystal lattice. And as I said, depending upon the orientation, you get block or nail wall. So you get these, the block stabilized system on this basis. Yeah. Anyway, what is the question?
Okay, but do we know why they're elliptical, or is there any idea about that?
Yeah,
circular.
Yeah. They're elliptical for the same reason that the helix we can see in different directions. So because of this and the underlying the Diriginsky-Maria exchange, it's this very interesting symmetry of these exchange interactions that causes them to be elliptical. So we know they should be elliptical. There's no reason why they have to be circular, because the circular nature is determined by the cubic. As soon as we go away from cubic symmetry, they no longer need to be circular.
Okay, thanks. And a practical thing, is this published? Because I haven't seen. I would like to.
Oh yeah, it was published recently in Nature Communications.
Okay.
The first author is Jana.
Okay, so the next question from Revas Ramasasvi. Please ask your question.
Greetings and thank you for the most inspiring talk. I have a question, in fact, even two, if the moderator allows me to. But the first question is, what is the experimental situation in centrosymmetric antiferromagnets?
Centrosymmetric antiferromagnets.
Because you spoke of lower symmetry systems.
Yeah, that's an interesting question. So let's say you take a cubic system like manganese-3 iridium. It turns out that actually has a chiral structure, a chiral antiferromagnetic structure, which has been observed even in relatively thin films by neutron scattering. And that chiral structure then, so just because it's cubic doesn't mean you can't have a chiral structure, but in that case, it can be clockwise or it can be anti-clockwise. They're equivalent. But you can, so what's super interesting, let's say we take a system like manganese-3 tin, manganese-3 germanium, which is a chiral antiferromagnet. And in these systems, you can change the chirality from clockwise to anti-clockwise by a small in-plane magnetic field, because the structure actually has a small uncompensated magnetic moment. And so the chirality of the structure is really important. It gives rise to, for example, to an anomalous Hall effect. So a system which has no net magnetization can give rise to large anomalous Hall effects related to the chirality. So you change the chirality from clockwise to anti-clockwise by an in-plane magnetic moment. You change the sign of the anomalous Hall effect. But interestingly, the spin Hall effect does not depend on the chirality. This is something that we first pointed out in manganese-3 iridium cubic system. Therefore, both chiralities are possible, but the spin Hall effect related to that chiral structure is independent of the chirality, so we can observe it. And we actually observed it. We were the first to observe it in a chiral antiferromagnet in manganese-3 iridium. So it's super interesting. These antiferromagnets are super interesting because of they have no net moment, but they can have a range of topological effects, if you like, including anomalous Hall effect, spin Hall effect, and other properties. Reflective.
And the presence of skyrmions?
Presence of, so they have not been observed yet, but very likely. They haven't been observed yet because in an antiferromagnet, there's no net magnetization. So they're super difficult to observe.
In principle there, but it's hard to see.
Probably you could see them optically because of the same systems, because they have these large Berry phases, they actually give rise to Kerr signals. So even though there's no net magnetization, they do have Kerr signal. And in principle, these Kerr signals can be quite large. And so maybe it's possible using SNOM techniques, if you can measure polarization, you could potentially observe them. So I think it's a super interesting question. There are ways of observing them, not yet observed, but I'm sure one eventually will see them.
Yeah, okay.
May I ask the second question?
I think there's a few here. Sorry, that I think I have a few here that are lined up a little while ago.
Then maybe later if there is time.
Later in a minute, yeah. So let me ask a question from Nguyen that unfortunately I cannot give the microphone because it's an old version of Zoom. What should be the electrical writing and reading components of SAF-based racetrack devices?
Oh, that's also a super interesting question. If I understood it correctly, how do we read and write into a SAF?
Yeah.
Well, SAF structure, one of its most interesting attributes is that even though in aggregate there's no net moment, the individual layers are magnetic. So you could write into one, let's say one side, the upper or lower magnetic layer in a SAF, you could use spin currents and you can write domain walls. This is certainly possible. And to detect them similarly, because the surfaces are magnetic, unlike a real antiferromagnet, then there's no net magnetization on the surface, usually because of steps. In principle, it's possible in, let's say, iridium manganese 3, you would expect to see a surface which is magnetic, but it's on the atomic scale. So steps means on aggregate there's nothing. But in the racetrack, because the upper layer is ferromagnetic, then the surface is magnetic, and you can just detect the domain walls by, for example, magnetic tunneling or other effects. So it's relatively straightforward.
Okay, good. So Helen, can you unmute yourself, see if you can work this time? Or not? Okay.
Sorry for the previous, it was technical problem. So the question is that you mentioned that if you use this platinum electrode, you can create this DMI in an antiferromagnet. So the question has to pass. First, did it work in this way? And what should be the property of the material? So can you do this with an insulating antiferromagnet, for example, and platinum electrode?
Yeah, I think there's a very interesting, and yes, the answer is yes. You can take, as you said, an insulating antiferromagnet, and in principle, by proximity, you can generate a moment in platinum next to it.
But how should you grow this? So is there some special conditions which you need to follow? So have you tried to do this?
Yeah, we're working on this, and we can do this. So, you know, it's like growing all these thin films. It turns out, depending upon the complexity of the material, like the Heusler compounds are super difficult to grow in thin film form. But we did achieve that. In my former group at IBM, we used something we called chemical templating layers, L10 materials, in which we were able to stabilize for the first time a single unit cell thick Heusler layer. It was a binary Heusler, but we can use the same technique for ternary Heuslers. So your question is a little bit unfocused. In other words, depending upon the system, let's say the chiral antiferromagnet, you can grow these using a variety of techniques, usually involving proper underlayers or templating layers that can stabilize the structure. In the case of this chemical templating layer we developed for the binary Heuslers, it means even when there are atomic steps in the chemical templating layer, we can stabilize a layer of the Heusler with no atomic steps. So it's quite interesting. It's quite amazing, actually. I'm not sure if that answers your question, but anyway.
That's okay. So let's move on to another person here. I have Daniele Komsky. Let me allow you to speak. Do you have a question for Stuart? Oh, sorry. I think I get the wrong one. Okay, Daniele Komsky.
Can you hear me now?
Yeah, I can hear you now. Sorry.
I have a question about the first part. You mentioned that when you have interface of cobalt and platinum and cobalt tungsten, the rotation is opposite. One is clockwise, another counterclockwise. My question is, what's the physical reason for that? I, of course, can simply say that it's different sign of the Lashinsky interaction, but optically, is it simply the difference between work functions? Because usually when you have interface of two metals, there's a difference of work functions. There is a double layer, potential energy drop, and internal electric field, and so on. Is it possible to say that they are simply opposite for cobalt platinum and cobalt tungsten?
So there's a wide variety of material combinations have been considered using cobalt and nickel and various elements. And even for the same, let's say, heavy metal like platinum or tungsten, depending upon the magnetic layer, whether it's nickel or cobalt, you could change the sign of the Dzyaloshinskii-Merea interaction. So I think I think there's no simple answer, but as you said, it's obviously due to electronic matching within the two layers, and this I don't think it's a double layer, but it's simply the electronic structure effects and how they are implemented. And so, of course, you can tune this by changing the the individual elements, or by forming binary or ternary alloys. And you could use this, of course. I think maybe your question is, in the end, not only can you change the sign, but more importantly, you can change the strength. And you can tune the strength significantly by alloying, just as you said, change band filling effects.
I think actually it can have very simple physical explanation, because what we learned studying multiferroics. Multiferroic gives you polarization if you have cycloidal structure, and depending on the rotation, clockwise or anti-clockwise, polarization is opposite sign. Now here it's maybe vice versa. So we have effective electric field on interface, and if electric field or potential energy drop is one sign, that will induce clockwise rotation, and if it's opposite sign, it will induce counterclockwise rotation. It's simply kind of inverse what we learned in multiferroic. I think it might be simple physics of it.
I think that's a very interesting point. I do believe that ferroelectricity and some of these interesting structures, there's a close correspondence between the two. So I think this is a very interesting point. It's something that needs to be investigated further. But thank you very much. That's a very interesting comment.
Not real ferroelectricity, of course, but simply just potential energy drop or internal electric field just at the interface. Opposite sign gives you opposite rotation.
Yeah, I think that's an interesting point. Certainly, yeah, okay. Fantastic. Thank you.
Yeah, very good. Thanks.
Thanks. And I think with this, I'm going to stop the recording. And if you kind of stick around a little bit, we'll answer the last few questions. But